Let's move on to the third presentation, the last one of this block, presenting my colleague at Dow, Valérie Hayez, Global Principal Scientist for our facade segment. Over to you, Valérie.
Thank you. Thank you for joining this presentation. So today I'm presenting on behalf of my colleague John. You all know John. Unfortunately, he could not be with us. Bomb blast is a topic that we really like at Dow. We've worked on it since a long time, starting with some physical testing that can be small test pieces, like you see here on the left, in a conventional HP setup, or in a special shape to allow shear deformation at high speed, to large mock-up field explosion tests. And in general, we can say that we observe an increase in maximum strength, stiffness, elongation, and tear resistance of the silicones when we are testing them at an increased movement rate. So we've used these data since the beginning to replace in our conventional analytical equations and to do joint dimensioning. But this comes obviously with some limitations. There's a variability related to the measurement. As soon as you start to increase your speed, you can have quite some challenges really with your equipment. And with the quantity of parameters you can vary in your testing. So the natural evolution, I would say, is to embrace the new tools that we have today, which are finite element analysis, mainly, giving you the advantages to be able to look at the complete system, including the frame, the glass, the interlayer, and then as a next step to really run a whole range of variations of these parameters or parametric analysis. Obviously, this also comes with some challenges because you need to develop advanced material models for every component, if you look at it. So the silicone, the glass, the PVB, the frame. You need as well to tell the software when it's going to fail. So you need still to do some experimental validation on a small scale. Test pieces you've seen, test it at high speed, and on large scale mock-up testing. So where are we at today? We have, as you may know, determined material models for most of our structural glazing, insulating glass sealants, and weatherproofing sealants globally based on normal pure deformation mode testing, so the uniaxial, the shear, and the compression test. And now to go further and to introduce the dissipation character, we are introducing relaxation test. With that, we estimate the Prony series, and we are going to check if with this model we can predict the observations experimentally at high speed. If it works fine, we have our material model for high speed. If it doesn't, we are working with some software to optimize the Prony series parameters until it fits. So we have published before already the material model for high speed for structural glazing sealant, the 993. We have identified the failure criterion, as I said, that we need to be able to tell there will be failure occurring in your model. And we are applying this now to more materials. So we've recently developed the material model in a similar way for 3363, which is an insulating glass sealant, as the industry is really asking us this as a next step, looking at the performance of an IG unit. So that's following exactly the same procedure, but still keeping in mind as well that this is nice, FEA, but we also want to have these ultimate tensile strength, elongation at failure for H pieces for different materials. So here you see that we are playing with most of our materials in the US. You will recognize them in Asia and in Europe. The two on the right here, every time, these are the 3363, so these are not SG, structural glazing, but they are IG, and that's why you see these big differences. Interesting, I think, to note is that at high speed, we don't see that much difference from material to material, these two accepted. And we could probably, when you go to simplified approaches, not really consider the silicone specifically. For a simplified approach, it doesn't make a big difference which material you're using here. Now, we also expand our testing our experimental testing with the goal of validating our finite element analysis. And so that's John's privilege. He has been able to attend these exciting test explosions at the University of Kentucky, whereas I do the fire test where nothing happens during 4 hours. So he's the lucky one. And we have really developed a testing protocol with the goal of breaking stuff. So, and we wanted different failure pattern. We wanted to break the both glass splice, but not the silicone. We wanted to break only the silicone. We wanted to break both of them, and we wanted also a situation where we broke nothing. So we varied our system parameters so that we could get to these results within what is possible to be tested. So we played with the pane aspect ratio, rectangular versus square, for more or less the same surface, with the frame material to have a more rigid and a less rigid one. The glass type was only one type. We had a relatively thin laminated glass with PVB, and the joint was also just one aspect ratio to limit the number of testing we do. We used an explosive charge in a blast tube, about 90 kPa, and the test units were 1.5 times 1.5 and more or less the same area, but in a rectangular configuration. 2 parts structurally glazed silicone, 12 by 6 normal joint design, and this is the glass built up. And here you see one of the units installed. So the first unit here, rectangular one, as it is installed, and I would have loved to show you the videos. We have all the videos, but they were quite big to embed in a presentation. So a few extracts of the simulations. We looked at the deflection values with the positive and the negative pressure, and we look especially at the peak effective strain in the silicone, because that is our failure criteria. So for this first build-up, we predicted nothing would really happen to the SG, and indeed, this is what we observed. We had the both glass breaking, but nothing happening to the structurally glazed sealant. So these tests have been done at low, high-speed video. So we have these so that we really can monitor very closely the breakage pattern for the glass, which was part of the research done with Arup as well. The second unit, a square one. Again, we look at the deflection, we look at the peak effective strain. We don't expect any failure. So yeah, that's also what happened. And there John got a bit nervous because these units are super heavy to lift and to install, and he really wanted to blow the stuff out. So he decided to flip the unit. And for this unit, have the blast act on in the other order. And there the prediction was that we would get failure, and this is indeed what we achieved. So the pane was nicely blown out, and we see here it's in front, a few feet, meter in front of the test facility, and we see here how the silicone has been completely disrupted. We tested the fourth unit, but unfortunately, well, nothing happened. We didn't even model this one. And here you have a little comparison. Again, it was not the goal to really vary parameters, but we still see some information about the influence of the material for the frame and how it affects the flexibility of the pane, and then, as a consequence, the strain, the peak effective strain on the joint. And similarly, the pane aspect ratio, how it can be affecting. So, conclusions from this preliminary work, we've seen when we did the FEA that it was really important to use highly discretized meshes, and that the peak effective strain was still a good criterion for us to predict when failure would occur. It would occur at the same place as in the testing. But we also observed that the glass model had to be really upgraded as well. And that's where Arup came in. I forgot to mention this was also a joint publication with Daniel Agromito and Will Holly from the New York office. They couldn't be there, so I very cowardly decided not to talk about it. I would invite you to talk with Graham, who is there, if you have questions specifically on this part. And it's also documented in the paper. So still, it's interesting, this FEA, but it's very heavy. We, TS&D, so support people at Dow, we need simplified approaches that will allow you to give very busy industrial people a quick answer. So we are trying to bring that knowledge in a simplified format that can be used directly. And so as usual, we are currently running a parametric analysis, varying a maximum amount of parameters, the glass dimensions, the PVB, the joint dimensions, so that we can, after that, extract some empirical analytical equations for the joint dimensioning. We are going through these. It's a bit slow. We are seeing stuff that is more or less normal, like increasing the joint height helps to reduce the peak effective strain, and that also the PVB has an influence. But for sure, we need to ask a little bit more patience, and maybe, yes, at next GPD, we'll come up with a finalized dimensioning guideline for bomb blast applications. So that's concluding my presentation. Thank you for your attention.